defects that can arise that happen in between 92-day inspections, and we like to catch them as soon as they come, as soon as they arise.
What would some of those be?
Say again?
What would some of the issues be?
Well, we could have traction motor leads come uncovered and become prone to shorting out, and that could be a major problem out on the road. Another issue is we could have a brake cylinder piston travel get it a little too long, and we could adjust that down before 92-day inspection so it doesn't get too close to being to an illegal amount of piston travel. We also check all of the fluids in our diesel engine. The prime mover lube oil, the cooling water. Another thing that we can check is the oil, the lube oil in the air compressor. We also like to bring them in the shop and clean them up so they're presentable. Since we are running passenger trains, we like them to look presentable. We recently moved into a new diesel shop built here on site in the Durango yard, and this last Monday inspection was actually our first time occupying the shop, and it went very well. We were able to since we were able to fit both MU diesels inside the shop at the same time, it shortened our inspection time by about an hour and a half. So we're pretty excited about that.
How long does an inspection typically last for?
So a weekly inspection will usually last, if there's no defects, if it's just an inspection, we can probably get through it in 3 or 4 hours. So, and that's running 2 diesels MU set, what we run on our trains here.
And how many people does that take?
We run a crew of 3 people, myself included, and it goes pretty quick. We've got it down to a science just about. So,
what kind of equipment are you going to be putting into the shop?
So we're still very, very new at this point in that shop. There isn't a lot of tooling or equipment over there quite just yet. We're still using a lot of the tooling from the other shop on site. That's going to change very soon. But as of now, we're just using what we have. I hear that we're putting a decent amount of machine equipment in there for like machining billets and all that, lathes and stuff like that.
In there, so this ought to work. That's great. Thank you. Great. All right. So where we're at now is over by the car shop, and also the addition to the car shop, the diesel shop and contract shop. These tracks coming off the loop here are all new tracks that were built in the last few months, leading to those new areas. So this track here is a rip track. There'll be another switch down further, so there'll be 2 rip tracks actually. This track behind me, running down the center, branches off to the diesel shop where the diesel locomotive is, and the center one goes right into the car shop where I work. And then there's another track behind that goes into the contract shop, and there'll be a crane track, they call it, or storage track to the side. So it's all brand new stuff, all pretty new for us. Probably our best track on the railroads right here. This is the brand new shop for diesels. I should say brand new diesel shop.
Brand new diesel shop, yes. Yeah, this will be the diesel maintenance bay. Had its first use last night, servicing one of the White Pass engines.
What's this space going to be used for?
This will be storage for parts, both for the car shop and possibly the diesel shop. It has a nice door out to the front patio where we can use a forklift to lift pallets of parts in here easily. Shelving yet. We'll probably run down the center and the sides.
The slope's on purpose, right?
Yeah, exactly.
Let you have all those nice angled parts.
So that's the original car shop roof. That's built, a new roof was built over on this whole side to create the drainage. Yeah. And then there won't be a balcony here or anything like that.
I don't plan on jumping either. Reminded the fall. I just hate the stops.
They're going to bust out 2 doorways into the new shop, so one of them will be right under here. So there'll be, you can cross, and this will be diesel part storage down here. I've been told. So we're next to locomotive 107 now. The truck we saw earlier in the machine shop came from this locomotive. Prior to us having a dedicated diesel shop, they had to build these pads out here to use these new electric jacks. When they lift up one of these diesels, they lift all 4 corners at once and then roll the truck out and can lower it back down. So this kind of work has been done on track 9 here the last few years. And that kind of work will probably be moving over to the new shop that we'll see later. Yeah, it's itself our Porter diesel that we don't use that much, but it's so it's a little bit different. It has spoked wheels, but you can see how these are all diesel wheels here with the
bearings that go in the gearbox for a diesel locomotive. We're making new ones out of nylitron. The old ones are brass. But these are going to the Colorado Railroad Museum.
Yeah, it's a little different. It needs a really sharp edge on there. It's like razor sharp as you can get the cutting tool. And it cuts fine. It's actually really entertaining.
What is the material again?
This is nylitron, or this brand of it might be Nylox.
And what is it used for?
It's highly abrasion resistant nylon, and we use that for bearing surfaces, such as this traction motor here. This will get, the bearings he's making now will get inserted into here. That's what this diesel motor will ride on.
Where are we now?
So this is our lagoon. It's just a pretty standard knee mill. We've got our nylitron bushing up in here. So we're going to finish some of the milling operations needed to be done on this nylon to get it to fit the axle and crankcase of the traction motor. This is very soft. It requires a much sharper tool. If your tool is dull, it tends to melt the nylon, versus a razor sharp tool is going to give you a nice clean cut, give you a very solid chip. It is extremely abrasion resistant. It is pretty comparable to brass. It tends to be forgiving in some ways as far as flexibility. It's less likely to crack, less likely to permanently deform. These are lubricated through the crankcase, and I believe it's indirect lubrication, just from what's being slung by the main gears in there. Yes, they need the same amount of lubrication as brass, and it tends to be lighter. It's a lot cheaper to get, and it usually is more available than brass. The brass ends up being specific alloys, and we need to find a foundry that's working with that alloy, where this can be ordered directly offline in any dimension you ask for.
I just looked in both the drawers and with the bin in, it wasn't in there.
Fair enough.
Just find incentives so I can split it. I know where to cut.
Gotcha. So Diego here is using a coaxial indicator to find the center of the bore on this bushing. He's then going to use the mill to mark the line where he splits this into two pieces so it can be applied and installed to the crankcase. I'm Jordan Green. I'm the machine shop lead here at the Durango-Silverton Railroad.
And how long have you been here?
I've only been here for 2.5 years.
How long have you been a machinist?
Been a machinist for just over 5. And yeah, this is our machine shop. This would be a 600-ton hydraulic press. We use this to press wheels off of axles, wheels back on. Many counterweights that have to come on. They come on and off in this machine. This was custom built specifically for this purpose right here and where it sits.
How do you set the wheels up in there?
We will hang the wheels themselves off of our bridge crane, and we'll hold the wheel. The axle goes on a bridge crane. The wheels are grabbed by the boom right here. So we'll hold the wheel up in place and use the big crane to line up the axle, and then we'll press that with the...
Where is the axle actually set in here?
And then pulling wheels off, this wall moves. So we'll move this wall forward. We'll put the wheel up against this face with the axle in the slot, and then we'll push the axle out of the wheel.
So that block for the wheel, these are the adjustment holes?
Yes. So all these holes just kind of let us move this wall to wherever we need for what job we're doing.
Okay.
So here you have some more new castings and parts for locomotives. These are actually tires that go on the drivers on some of our engines, probably the K36s. You notice they have the flange on them, and they'll put these on by heating them, expanding them, and they slip them over the tire, the inside part of the wheel, and then as they cool, they just adhere themselves to it. Again, that's all that's fastening that tire to that center. And then these could be turned several times as they wear out until you get down to the condemning limit. It gets too thin, and then they start the whole process over again. I have a stack of axles off of various cars. Axles could actually be reused over time. You go from a large 5x9 axle, and it gets down to the condemning limit on the outside wear surfaces. You can turn it, the whole thing smaller, and make a smaller axle out of it. So it may look used and not usable, but actually these could be recycled probably. Here you have tires, again, blind drivers and flange drivers for the locomotives. These wheels here are probably 28-inch wheels for coaches or for pony trucks on the locomotives, and these are the kinds of wheels when they come brand new for us, for our coaches. This is what we get them like. We get all our wheels, I believe, still from Pennsylvania. And it's not many places that make wheels. They have to custom make them because this is a small bore, the hole. And again, that has to be machined out exactly to fit each axle that we want to press on it. So it's not a real quick deal, but they're custom made in pairs for each wheel.
Had 7 hookers and stole the fire truck. And it took them about 5 hours to wrangle us to get us apprehended.
This is a 14-inch grinder. It's primarily used to sharpen drill bits and tooling. 40-ton and 100-ton press. This gets used primarily to press the brass into the counterweights. Any bushings we have, that's primarily what's getting used to press those into their correct location. And with this, with our brass fits, we usually have 1.5 thousandths per inch of interference. With steel on steel fit, it's 1,000th per inch interference. And we usually, the pressure varies depending on the diameter of what we're pressing, but 5-inch diameter we'll usually press on at about 40 or 50 tons. And that's with 1,000th per inch of interference, so 7,000ths interference. Yes, 1,000th per inch of diameter interference. Oliver here is making pins for the lead truck of the 722 in the Great Smoky Mountains. So we've got about 16 pins to make as we utilize a smaller lathe. That's just kind of allows us to keep our production up higher. We're not spending as long moving heavier, larger lathes around. All right, these parts here, they're hangers for our roller bearing truck conversions. We're in the process of converting some of our brass and Babbitt bearings over to roller bearings, which are usually provided by Timken. And these are what ends up holding the pedestal that the Bissell post would ride on a lead truck. This is our Pratt & Whitney vertical slaughter. This primarily gets used to put keyways into our rods. This machine is fairly old. I'm not sure of the exact date that it was manufactured, but it was, to my knowledge, manufactured in the early 50s. It doesn't get used frequently here, but there are jobs that this does that none of our machines are capable of doing, such as putting a keyway into the rod. And it is a very solid machine. We keep using it because they don't build them like they did, as well as preserving the history of the locomotives and the railway. We really enjoy preserving the history of the machines behind all of the work. So that's a main reason that this still gets used today. So this is your cutting edge right here. And this machine, it will move.
So it cuts vertically.
Yep, it'll cut vertically. As it's stroking down, this edge will cut, and as it pulls up, that retracts, and that will relieve the tool from the cut and let it move on to its next cut.
And are the eyeballs extra?
Those are extra. It does a pretty fun dance moving up and down and moves fairly rapidly, so the eyeballs just ended up being something fun for us.
Okay, where are we now?
All right, this is our Carlton drill press. It's a radial arm drill press with a 15-inch column. This was another one that was owned by the U.S. Department of Defense. It was bought by us through an auction. Not specific on the date that it was manufactured, but it was war baby, so it was working for World War II in the prime of its life before it got here. And this is used, we will drill the crank pins out of counterweights with it. We'll use up to a 3-inch drill bit. From that, anything down to an 1/8-inch drill bit, it'll run them all the same. This is our Bullard Cutmaster VTL. It's manufactured in the mid-60s. It is a hydraulic vertical turret lathe. We have 5 tool positions on here, as well as a 36-inch chuck. And all of the movement is run hydraulically, short of the chuck itself is driven via gear.
When you say 5 tool positions, what do you mean?
This turret here rotates, So we can put 5 tools on the end of this turret, flip a knob over there, and it'll switch to the next one. And that allows us to complete multiple operations without changing our tool, without taking the time to remove the boring bar, put a different one in. With the side here, we can also do facing and OD operations. Primarily, the turret itself is used for ID work inside pipe or with this machine, we generally do driving boxes on them. All of our smokestacks get fit up on this machine. That's the primary use for this one itself. Our other bullard is where we do most of our wheel work.
What is this part?
This is a throttle from our 482. It's currently undergoing restoration. The throttle itself has been rebuilt and relapped, so it's good to go. All this needs is the rest of the engine put together, and we can put it in there.
And what are these parts?
So these are the rods. This one specifically is the main rod. This attaches directly to the piston and crosshead of the engine. This is what's transferring all of the steam power into rotational power. So in this, we have bronze bushings. The holes are for grease. So this rod is upside down at the moment, but this grease fitting here gets hard grease, and these holes allow the grease to flow through to the pin on the counterweight. These bushings are called floaters. They freely move, so they have plenty of room to rotate. It reduces friction and reduces temperature. This is a clearance fit. We have a clearance of about 10 thousandths of an inch, and that allows this to move freely without banging around, without having too much slop so that it rattles when that counterweight changes direction.
So the shaft is rotating in the bearing, and the bearing is rotating in the rod.
Correct. These two here are mid-connecting rods. They connect our number 3 and number 2 drivers together. And these knuckle pins connect to the number 1s. The other side connects to the number 4.
How did they get the name knuckle pin, do you know?
Because it very similarly resembles a knuckle. As your knuckle would move like that, these allow your number 1 and 4 rods. They allow this piece of the rod to rotate up and down, but don't allow it to rotate or move laterally. All the brass in here, it's cut to 1 1/2 thousandths of an inch interference. So for a 5-inch hole, we would have a 7 thousandths interference fit. And these get pressed on
the inside, right?
Yes. These get pressed on in the press shown previously. These keyways here, that keeps the brass, when we press that in, there is a lot of force undergoing that, and that just keeps that brass from rotating out. As they wear unevenly, and they tend to wear front to back instead of up and down. So if that rotates, that could create a problem with the timing of the engine.
So why don't you need a keyway on the other end?
Because the larger surface area has the potential to build more friction. We get more longevity out of the brass if we let that free float and rotate on the pin and inside the rod. We usually get 2 seasons out of each bearing. It depends on how hard we are on the engine and how long the engine runs, but we can guarantee a season out of a new set of brass, it'll usually run 2 seasons. All right, this is our Lucas 42B. This machine is actually 2 machines dressed up in a trench coat as one. So we have the saddle, base, and backrest of a 42. We have the spindle of a 42B. This was originally built in the late 40s. It was then rebuilt by General Electric in '53. Primarily use this for boring holes, given a horizontal boring mill. This lets us bore 2 concentric holes through a frame and keep them in line with each other and correct. Yeah, the table will move. We have our y-axis going in this direction, our x-axis in this, and we've got essentially a Z right there. The other benefit of this machine is the length of spindle it has. This spindle, I believe, is 5 feet long, and it allows us to reach parts in castings that our other mills can't reach or can't quite access. Another view of our Craven quartering machine, which stands right next to our Cincinnati number 4. The Cincinnati number 4 was built in 1953 is the nameplate on that. It is an extremely rigid and reliable mill. This is my personal go-to with any milling projects. It is very sturdily built. So it doesn't, most machines will flex a little bit. They'll move. They have a little bit of slop here and there. This machine, running more than 70 years, has been invaluable to us at the railroad. And with the high rigidity of this machine, it lets us hit tighter tolerances. It lets the cut run a little truer than an older machine that's had more wear on it. So this is our 48-inch American super productive lathe. We primarily use this for recontouring the wheels. We have a hydraulic tracer that will trace the exact contour of the wheel. So once they hit a point of wear, we are required by FRA standard to recontour them to give them a new life, and we can generally recon a wheel set 4 or 5 times before it becomes condemned. So on this American Cutmaster, we have a very large tailstock. This actually gets moved by a gearbox that's right down here. That is due to the weight of it. It needs a gearbox to help manipulate the location of that. Behind the tailstock, we can see a steady rest. We use this to support long material that tends to sag under its own weight. It ends up being extremely hard to cut long material because of its flexibility. It'll push away from your tool, where we would bring this steady rest in to support the middle of our workpiece while we machine around the steady rest. This here is our cross slide. It is not a traditional cross slide. It is not the one it came with. This has a hydraulic tracer attached to it made by Mimic Tracers, who's no longer a functioning company. It uses this stylus here to trace this template, which is the ideal profile for our wheels. We have different templates for different wheels. Tender axles need a wider flange than car axles do. The workpiece here, we have a 48-inch chuck. We can fit a 49-inch piece of material in that. And the length of the bed, I believe we have 15 feet of length that we can utilize. So this is our Bullard vertical turret lathe. It is a spiral drive. This is one of my favorite machines in the shop. It was built in 1941 and bought by General Electric. In 41, it was sent to England on a loan lease, so that started producing for the World War II effort before the U.S. got officially involved. It still uses a 21-foot leather belt to operate the rapids as far as what location you want your tool to be in. And it is a very thick, sturdy leather belt. Down here we can see the counterweight. The counterweight itself is to help mitigate the weight of our turret. So that helps counterbalance when we want to lift this turret up. If we want to bring it down, that makes it nice and easy for us to turn a hand wheel manually or for the leather belt to drive the rapid.
When you say spiral drive, what did you mean?
We can actually see it right in here. So there is a big gearbox underneath our chuck. Our chuck can handle 48 inches of material. We can get just over 3 feet in height from the chuck itself. The spiral drive is the way it feeds and the way it turns our chuck, where we can see, if you can get the camera in right through there, you can see that it's a worm gear or a spiral gear. And that's what's driving your feeds for the cutting tool to move through your part. There's a very similar gearing in the gearbox underneath the chuck. So these boxes here are the gearboxes for our feed rates on our cutting tools. These handles here control our spindle speed or our chuck speed. This box over here is a mechanical lubricator. So you can see the oil moving through here is a visual check to make sure that we do have oil going where it needs to and that it is coming back to the reservoir. This is our second American Super Productive. This also has a 48-inch chuck. It is almost identical to our previous one. This one has a 6-inch riser right here to allow us a larger work diameter. So with this, we are able to put up our drivers and we'll be able to recontour the driver's surface on this machine. This has another tracer on it made by a different company that has a slightly different mechanism. Both of these Americans were built in the 1930s. They are very old. They're very hard to work on because not much of it has been taken apart since the 30s. This is our Lodge and Shipley. It's been a great lathe. I'm not sure of the manufacturing date on it. My understanding is this also came from the mid-60s. We don't utilize the length of the bed completely. Going back to the rigidity of the machines, this machine isn't as rigid as it used to be. So we can't get those long work pieces that we could in one of the other larger lathes. But this lathe does give us the capability of a 13-inch diameter and up to a 12-foot length on the bed. This is our American lathe. It's a lot smaller than our other Americans. We use this primarily for making stay bolts for the boiler. It deals with a lot of our smaller work. This one was built in the early 1950s, and it is one of our most accurate machines we have in the machine shop. This is where most of our threading gets done because it just has a little more rigidity than some of our other lathes. As well as stay bolts, we do a lot of our rod brass in here. That and all of our valve work and tapered work is done in this lathe. I got my start in machining with CNC machining. That was up in Portland, Oregon. I worked for Oregon Tool, and I really enjoyed that. But history has always been a larger passion of mine. I like working with historic tools, historic machines, the locomotives. That's what really drew me to this shop over any. And you can see that nothing in our shop has a digital readout. So everything is done manually. The only digital things we generally have in here is a calculator and our digital calipers. Everything else is done as close to the way we can do it as they did when these engines were built.